Hello everybody. My name is Ferdinand Gerhardis and I'm acting as Business Development Manager for the Anritsu EMEA Engineering and Technology Group. Here today I would like to give you a brief overview about how to post-process a 5G new radio signal that was IQ captured by the MS2090A Spectro Master Pro and is finally post-processed with BIRD Technologies Spectro X software. Based on a real 5G new radio field measurement, we will present briefly how to capture a 5G signal. After that, we will explain the nomenclature of an IQ file and its format. Subsequently, and after proper conversion, we will load the captured signal into the BIRD Technologies Spectro X software and replay and analysis time-wise and frequency-wise the signal. We will close this short podcast with a brief introduction into the Spectro X feature set and a demonstration of a real-world 5G new radio signal. Here, on this slide, we see the demodulation results of the MS2090A 5G new radio summary multibeam feature. It is obvious that the measured 5G antenna is radiating 7 beams, as you can see here, where beam number 7 is providing with minus 54 dBm the strongest signal at the measurement location. Besides, the observed signal interference noise ratio is 21 dB, which is indicating a very clean signal. Somebody can assume that the measurement location is also very next to the beam number 1. This assumption is supported by a good power level of around minus 70 dB and again an SENR that is with 25 decibels even superior. In order to initiate an IQ capture of such a 5G new radio signal, you just enter the MS2090A file menu and you tap on this button 5G capture. This operation is taking a 40 milliseconds lasting time record of IQ data, which is finally saved into the internal memory. The resulting file name looks a little bit cryptic. The file is a 32-bit floating point file format that contains one after the other, first the I and then the Q values. An advanced user can easily import these files into standard MATLAB applications, using here these simple routines. The file is built out of date and time, GPS, PPS offset, center frequency in Hertz, and the sampling rate in samples per seconds. That's all. During post-processing, many users would like to see the offset of the SSB blocks from the center frequency and the timing behavior. That's why we focus here mainly on the explanation of the synchronization signaling blocks, called SSB blocks. In the time domain, the first symbol of an SSB burst is the primary synchronization signal. The second signal is a physical broadcast channel. The third symbol is the secondary synchronization signal, and the fourth symbol is again the physical broadcast channel. To enable the beam sweeping of synchronization signal and PBCH, the transmission of SSB blocks is organized in a periodical series of SSB burst sets, such that the transmission of SSB blocks within the SSB burst is confined to a 5 milliseconds window. This is equal to half a radio frame. Within this 5 milliseconds window, and depending on the use of the relevant subcarrier spacing, a number of possible candidate SSB bursts are transmitted. There are in total 5 different categories, A until E, in process to identify the SSB start symbol index. In our example, we will later on see that our signal is following the scheme number B. Each SSB block within such a 5 millisecond SSB burst period is assigned with the unique numbers starting from 0 and increasing by 1. This number reset to 0 in the next SSB burst after a typical transmission cycle of 20 milliseconds. This unique number is informed to the user equipment and is the so-called beam index. The illustration of SSB transmissions shown above is the case where all the SSBs are transmitted. But it's not required to transmit all the time all SSBs. Depending on network requirements, it can selectively transmit only a few SSBs and inform the user equipment of which SSBs are transmitted and which are not transmitted. Spectro X is the versatile software that allows users to visualize and analyze up to 4 independent recorded IQ signals simultaneously. It is a valuable tool for system and test engineers developing and analyzing conventional radar, ELINT, SIGINT, ECM, ESM, multi-channel communications, telemetry and MIMO systems. In the following example, we will use Spectro X in order to post-process and characterize a 5G signal in time and in frequency domain. First of all, it is possible to display the entire signal length in a power versus time representation, showing max, average, and min traced. Next, you can see power versus time, but this time in a free, scalable time axis. In the top right window, you see a density spectrum, very similar to a real-time spectrum analyzer density display. In the bottom right corner, you see a spectrogram view. All the 3 before mentioned displays can run by using faster or slower speed. This is equal to different zoom factors. Via the menu bar, it is possible to display again a spectrogram in time display. But this time, the user can scroll in predefined steps across the signal. This slide shows the final results of our measurements. The following video sequence gives you a live impression how easy such analysis can be for you. First of all, load the converted file in a Spectro X readable XDAT format and next arrange the settings either manually or, as we do here in our example, just load a predefined setting file. Finally, play the file on different zoom levels and operate the markers or other analysis features for a more in-depth signal analysis.